Hello, welcome back to three-phase circuit analysis. We're doing Wye-Delta problems. This is kind of a monster problem a little bit. Once we do it, you'll be able to understand where the steps involved and it won't seem so bad. But at first, the first time you see one of these problems is a little daunting, and that's why I wanted to show you this. So let's just read it. We'll have to draw some things, we'll have to talk about some things, but this is a good test question. So we have a balanced delta load that has an impedance of 216J63, that's a delta load, and it's connected in parallel with a Y load that has an impedance of 50 and an angle of 0 ohms. Right there, that first sentence seems weird, because not only do you have a delta load, but you also have a Y load, and those two loads are connected in parallel. So we've never done a problem like this before. We did do a problem a while back where one leg of the delta load had like a little tiny parallel part. This is different. This is saying we have an entire delta triangle and an entire Y-connected load. Those two loads are physically connected in parallel to the transmission line. That's what that's saying. Okay? The delta load is fed from a line of impedance, here we go, 0.5 plus J4. That's easy, that's just a line impedance. And then it's telling us the magnitude of the line to neutral voltage of the Y load is 750 volts. So again, that's kind of a weird, because you have two loads to think about, it's weird. But if you think about it, if you just ignore the delta load for a second, just pretend there's no delta load at all. If this were just a YY circuit, then this makes sense. The magnitude of the line to neutral voltage of the Y load, we could draw a single phase equivalent circuit, we could figure out what the line to neutral voltage is, and that the magnitude of it's 750. Notice they don't give us a phase angle, and they don't tell us to take anything as a reference. So we're just given the magnitude. We're going to have to make some assumptions along the way to solve this problem. All right. Now we have four things we want to find, and every one of them is just to find the magnitude of something. So when I told you the rule of thumb before, in a problem when it just tells you find the magnitude of something, two things you need to think about. Number one, you probably weren't given enough phase information to begin with to be able to find the full phasor representation of all the stuff we're trying to find. So that you're probably going to have some information missing from the problem, and in fact we do. We don't know if we don't know the phase of this voltage, for instance. So we have to make some assumptions. And number two, you're going to probably, you need to, when you do your calculations, you make whatever assumptions you can and carry your complex numbers down all the way as far as you can to the end. Don't start throwing phase information away from your impedances and stuff, because some people think, well, if I only care about magnitudes in the end, I'm just going to find the magnitude of these impedances and just use that. Don't do that. You got to keep the complex number arrangement of everything intact. Make an assumption here at 0 degrees if that's what you have to do. Carry your complex number calculations to the end. Then at the end, throw the phase away and just keep the magnitude and circle the magnitude. That's going to be a lot more bulletproof than trying to figure out what you can throw away and what you can't in your problem statement. All right, so we have a parallel combination of two weird-looking loads. And then what do we ask to find? The magnitude of the line current feeding the loads. Okay, so we have a transmission line. It's going to be feeding two loads. We want to find the line currents. We want to find the magnitude of the phase current in the delta load. These are the currents that are circulating in the triangle, the phase currents. And then we want to find the magnitude of the phase currents in the Y load. These are the currents that are going through each leg of the Y load. And then we want to find the magnitude of the line voltage at the sending end of the line. In other words, there's a generator here somewhere off on the left-hand side of the circuit, and we want to find the line voltage, VAB, VBC, VCA. We want to find the magnitude of those guys. Of course, the magnitude will all be the same for the three different line voltages, but in other words, we don't care about the phase. We just want to know what the magnitude is. Okay. The other thing that jumps out at you right away when you look at this problem is you're given the delta impedance, each leg of the delta triangle in rectangular form, but you're given the Y load impedance as a weird thing. Usually you don't see impedances as magnitude of phase, but you can convert this to rectangular. And what is it, by the way? If you have 50 as a magnitude at an angle of 0 degrees, that means that impedance lies on the x-axis. Which means what? It means it's real. There's no imaginary part to it. If the angle is 0 for the impedance, there is no imaginary part. It's not up and down, it's just completely horizontal. That means that this is a fancy way of writing 50 ohms. You see, this is a great trick that a professor might throw at you and say, give you this, and people might freak out and say, whoa, I've never seen a phase like that. This is just basically, I could have rewritten it and said, hey, it has a Y impedance of 50 ohms. Well, that's boring, but this makes you think a little bit more. What does this mean? It means 50 angle 0 means 50 ohms. No imaginary part, no inductance.